A particle could be traveling from the future into your past right now. That's the tachyon. It's a serious idea from physics, from the very edge of it, and it challenges what we know about time. A few lines of mathematics can threaten the logical foundation of the universe. That's what we're looking at. This idea escapes science fiction. It has meaning for cause and effect. Brilliant minds have spent decades hunting for it, a ghost in the cosmic machinery. The past being set in stone, that's the question. To understand why that's strange, you need the rules. There's a speed limit in the universe. It's built into reality. Nothing that has mass can ever get to the speed of light. When something speeds up, its mass grows. It needs more and more energy to keep going. To get a single proton to light speed would take infinite energy. It can't be done. For us, light speed is a wall. You can't break through, but math has a way of asking questions. What if the wall wasn't there? Instead of trying to push something to that speed, what if you just imagined a particle that was already moving faster? That's the tachyon. It doesn't accelerate to that speed. It's just born there. It exists in that state, permanently faster than light. If you take the equations of special relativity and apply them to that kind of object, you get something bizarre. Its mass becomes what physicists call imaginary. That's a mathematical term. It means a number multiplied by the square root of -1. And more than that, its relationship with time flips. From our point of view, a tachyon's clock would seem to run backwards. It's not just fast, it's alien. It operates under different temporal rules. This isn't science fiction added to physics. It's a direct consequence, an unsettling one. It comes from taking our best theory of motion and asking it a question it wasn't built to answer. The tachyon is the answer. It's the universe whispering from the other side of the light cone. In the 1960s, that whisper became a formal proposal. Gerald Feinberg, a physicist, was looking at the bedrock equations of special relativity. The ones that tie energy and mass and speed together. He followed the math where it led, even into places that didn't seem to make sense. You know the famous equation, E = mc². But that's the simplified one. The full equation has a term for momentum, for motion. And when Feinberg solved it, he found it allowed for two families of solutions. One family describes everything we know: stars, planets, people, objects with real mass that can never reach light speed. But the other family, mathematically just as valid, described something else. It required the particle's rest mass squared to be a negative number. In our world, mass is positive. You can't have -5 kilograms, but mathematics has tools for this. Numbers that involve the square root of -1. Imaginary numbers, so in this framework, the tachyon would have an imaginary rest mass. It's not a physical substance you could weigh. It's a mathematical label, a property that forces the particle to live its entire existence on the far side of the cosmic speed limit. It doesn't accelerate past light speed. It simply cannot go slower. The equations demand it, and this is where time gets tangled. You plug an imaginary mass into the relativistic equations, the ones that govern how clocks tick for moving objects. A strange inversion happens. For a normal particle approaching light speed, time dilation stretches its seconds out. Its clock appears to crawl from our perspective. But for a tachyon, the equations suggest its internal clock would appear to run backwards relative to us. In certain reference frames, it would be emitted in the future and absorbed in the past. The mathematics doesn't just permit faster than light travel. It couples it, inextricably, with a reversal of time's apparent flow. This isn't a violation of Einstein's theory. It's an extension of it, a shadow realm the theory contains but our reality seems to lack. The equations act as a doorway, and they're standing wide open. They hint that our perception of a single, relentless forward arrow of time might be a local condition. Not a universal law, it forces a question. If the math so clearly points to a possibility, why does our universe seem to hide it from us? What would it mean if the most fundamental properties we associate with reality, like mass and sequential time, aren't absolute. If they are just the settings of the particular corner of existence we inhabit, the math gives an answer, but the answer only deepens the mystery. Einstein's theory of special relativity built a new structure. It joined space and time into one thing, spacetime, and it set a limit. A universal speed limit. The speed of light, see, that's not just a speed, it's a constant. A property of the universe itself. Nothing with mass, nothing carrying information, can go faster than light through spacetime. This limit isn't random. It's what makes cause and effect work. Like dropping a stone in a pond. The ripples move out at a certain speed. Light is that ripple in spacetime. Any event creates a ripple of influence. And that ripple can't outrun light. That idea gives you a light cone. For any point in spacetime, the cone defines what can affect it, and what it can affect. Inside the cone, events are connected. Cause and effect are possible. Outside the cone, they're separate, causally disconnected. That structure is why time feels like a one-way street. Effects follow causes, the past is fixed, the future is open, we move through it at a steady pace. That's the universe we know, it feels absolute. But the mathematics of relativity, the same equations that build this causal structure, they contain a hidden door. If you solve them completely, they give another set of solutions. These solutions describe particles for which the speed of light isn't a maximum, it's a minimum. They can't go slow. For us, light speed is an unreachable ceiling. For them, it's an impassable floor. They don't accelerate past the barrier. They exist on the other side. A mirror realm, an inverse universe inside our own. In that realm, the most basic rule of our experience is flipped. And if the rules of motion are inverted, what happens to time? The equations suggest for such a particle, the flow of time as we see it would be inverted too. An event we call its creation might, from its perspective, be its end. This isn't just about speed, it's a rewiring of sequence. It forces a question, is our arrow of time, our sense that cause comes before effect, a universal truth? Or is it just a local condition, a consequence that everything we're made of travels slower than light? The Tachyon idea doesn't just add a particle. It uses the universe's own rules to ask if the rules we count on are the only ones possible. The Tachyon idea runs right into cause and effect, a basic rule. If a particle could carry a message from the future to the past, you'd get a logical knot. Something the universe can't untie. The grandfather paradox is the classic example. Say you send a tachyon signal back. One instruction, prevent a specific meeting. If that meeting was your grandparents' first meeting, then you're never born. But if you're never born who sent the signal, the instruction creates its own impossibility, a closed loop. No beginning, no end. The event that caused the signal gets erased by the signal itself. For physicists, this is serious. It's a violation of causality. Cause must come before effect. Everything we understand, physics, history, daily life rests on that sequence. A tachyon, as an information carrier, doesn't just go faster than light. It threatens to unravel sequence itself. Let an effect reach back and eliminate its own cause. So you have a choice. Either these particles can't exist, because the universe prohibits paradoxes, or our understanding of cause and effect is wrong. Maybe paradoxes aren't possible. Not because time travel is forbidden, but because the timeline is resilient. Some theorists think the universe has a self-correcting mechanism. A cosmic editing rule. It makes sure all events, even ones influenced by messages from the future, weave into a single, consistent story. No true contradiction. The past you try to change might already include your attempt to change it. You end up with the very present you started from, that idea. A fixed, self-consistent timeline offers an escape. It suggests the tachyon, if it's real, might not be a tool for rewriting history. It might be a thread already woven into the tapestry, a part of the story we just haven't read yet. The universe has to protect its own logic from these knots. There's a principle for that, a kind of cosmic consistency. It's named for Igor Novikov, The idea is simple. The universe is a self-correcting story. It can't contain true contradictions, so any action that looks like it could create a paradox, like sending a signal to the past just can't happen. Not because something physically stops it, because it's logically impossible in a consistent timeline. You couldn't change the past. Your attempt to change it was always part of the past. Your future action is woven into what already happened. Think of a novel where the ending is already written. A character in the final chapter decides to send a warning back to chapter 1. But if you flip back, that warning was already there. It was influencing the story all along. The character didn't change the narrative, they fulfilled it. Their free will wasn't taken away. Their choice was just the mechanism the story used to become what it always was. Apply that to a tachyon. Imagine one arrives today carrying data from tomorrow. The Novikov principle says this event isn't an intrusion, it's a completion. That tachyon's journey from its emission in the future to its absorption in our present was always a fixed part of history. The information it carries has already shaped the world, guiding events toward the very future that will emit it. There's no first cause in the loop. It's a closed circle of influence, perfectly consistent, no loose ends. This paints a deterministic picture. The cosmos becomes a single, self-consistent block. All events are fixed in relation to each other. Our perception of an open future, of free choice, might be an illusion we experience from inside the story. Or maybe our choices are real, but their outcomes are woven into a grand, non-contradictory tapestry. A tapestry we can't see in full. For the tachyon, this principle offers a possible home. It isn't a paradox machine, it's a consistency enforcer. A particle traveling backwards in time isn't breaking the rules, it is the rule, a stitch in time ensuring the fabric holds. The principle doesn't prove tachyons exist, but it answers the most damning argument against them. It shows how a universe might allow backwards in time influence without tearing itself apart. The real mystery shifts then. If such particles are weaving through history right now, how would we ever know? Their influence would be hidden in plain sight. A secret cause already baked into every effect. Long before they showed up in physics journals, tachyons were already in our stories. The word has a certain sound to it: speed, the future. It really came into popular culture with Star Trek. In that world, tachyon beams weren't theoretical. They were tools. A starship would use a tachyon sweep to find a cloaked ship. Weapons fired tachyon pulses. It was a useful piece of technobabble, a particle that could carry information faster than light to fix a plot problem. A brilliant shortcut. The writers took a real scientific term and gave it a job their universe needed. And from there, the idea spread. In novels, films, video games, tachyons became this universal symbol for breaking rules. They'd power impossible drives, send messages across millennia, open windows into other timelines. In these stories, they usually didn't come with the baggage, the imaginary mass, the inverted time. Their strangeness got simplified down to pure speed. A magic ingredient for going beyond. That cultural footprint matters. It shapes how we first imagine the concept. When you hear tachyon, you probably don't picture a mathematical term in an equation. You think of a shimmering beam on a view screen, a ship vanishing into hyperspace. That glosses over the profound and honestly unsettling physics of the real proposal. But it points to something deeper than scientific accuracy. It shows a persistent human fascination. A longing to get past the most basic constraints we know. The limits of space, the one-way flow of time. Fiction takes this raw, abstract possibility from the edge of physics and gives it a face. Makes the desire tangible. That desire, to peek around time's corner or leap across the galaxy, isn't so different from the curiosity driving a theoretical physicist. One builds narratives with starships. The other builds narratives with mathematics. Both are exploring the same question. What if the walls of our reality aren't as solid as they seem? The popularity of tachyons in stories created a kind of loop. It made the name familiar, which then fueled public interest in the real science. People wanted to know if the particle from their favorite show could be real. That brought a wider audience to the profound implications sitting inside Einstein's equations. The fiction, for all its liberties, acted as a gateway. It prepared the cultural soil for a much stranger seed to be planted. The genuine, rigorous, and paradoxical search for a particle that lives backwards. That cultural fascination had to meet the hard ground of experiment. If tachyons are woven into the cosmos, how would we ever catch one? The hunt requires physicists to think like detectives, looking for the crime scene of an impossible particle. Since tachyons wouldn't interact with our world in normal ways, you can't just build a tachyon trap. You have to search for their ghostly signatures, the disturbances they might leave behind. One promising clue comes from a familiar glow. When a charged particle, like an electron, moves through water faster than light can travel in that water, it produces a shockwave of blue light. This is Cherenkov radiation, the eerie luminescence in nuclear reactor pools. It's the optical equivalent of a sonic boom. For a normal particle, this only happens inside a medium like water or glass, where light slows down. But a tachyon is different. It's born faster than light even in the empty vacuum of space. So theorists ask, could it produce its own version of a shockwave? A vacuum Cherenkov radiation. This would be a completely new kind of light, emitted into empty space by something moving too fast for the universe's ultimate speed limit. Detecting that unique radiation signature would be a smoking gun. Experiments have scanned the skies, looking for unexplained bursts of energy that match this impossible profile. So far, the vacuum remains silent. Other searches dive into the chaotic rain of cosmic rays. These are high-energy particles from deep space, constantly bombarding our atmosphere. The data from cosmic ray observatories is a treasure trove of strange events. Physicists meticulously sift through it, looking for anomalies that defy all standard explanations. An interaction with the wrong energy, a particle appearing from the wrong direction, an event that seems to violate conservation laws. Any of these could be the faint fingerprint of a tachyon zipping through our detectors, interacting for just an instant before vanishing backwards along its own timeline. The meticulous work has turned up intriguing oddities, but nothing that can't be explained by conventional, if rare, processes. No undeniable tachyon has announced itself. These null results are not failures. In science, knowing where something isn't is as crucial as finding where it is. Every experiment that comes up empty places a new, stricter limit on the tachyon's possible properties. It tells us that if tachyons exist, they interact with our world so weakly, so rarely, that they are effectively ghosts. They don't shape the cosmos in any way we can perceive. This pushes the idea further from tangible physics and deeper into the realm of pure mathematical speculation. The hunt continues, but with each passing year of silence, the tachyon becomes less of a potential particle and more of a profound philosophical question. It asks us why the universe seems to have drawn a line at light speed, and what it means that the mathematics so clearly points to a world on the other side of that line, a world that remains stubbornly, mysteriously, just out of reach. So that cultural fascination had to meet the hard ground of experiment. If tachyons are woven into the cosmos, how do you catch one? You can't build a trap. They don't interact in normal ways. You have to look for the ghostly signatures, the disturbances they might leave behind. And one clue comes from a familiar glow. When a charged particle moves through water faster than light can travel in that water, it produces a shockwave of blue light, Cherenkov radiation, the eerie glow in a reactor pool. It's an optical sonic boom. For a normal particle, that only happens inside a medium where light slows down. But a tachyon is different. It's born faster than light, even in the vacuum of space. So the question is, could it produce its own shockwave? A vacuum Cherenkov radiation. A new kind of light, emitted into empty space by something moving too fast for the universe's speed limit. Detecting that signature would be a smoking gun. Experiments have scanned the skies, looking for unexplained bursts that match this impossible profile. So far, the vacuum is silent. Other searches look at cosmic rays, these high-energy particles from deep space, constantly bombarding the atmosphere. The data from cosmic ray observatories is full of strange events. Physicists sift through it, looking for anomalies, an interaction with the wrong energy, a particle from the wrong direction, an event that seems to violate conservation laws. Any of these could be the faint fingerprint of a tachyon, zipping through a detector, interacting for an instant before vanishing backwards along its own timeline. The work has turned up oddities, but nothing that can't be explained by conventional, if rare, processes. No undeniable tachyon has announced itself. These null results aren't failures. In science, knowing where something isn't is as crucial as finding where it is. Every empty experiment places a stricter limit on the tachyon's possible properties. It tells us that if tachyons exist, they interact so weakly, so rarely, that they're effectively ghosts. They don't shape the cosmos in any way we can perceive. And that pushes the idea further from tangible physics, deeper into pure mathematical speculation. The hunt continues, but with each passing year of silence, the tachyon becomes less of a potential particle and more of a philosophical question. It asks why the universe seems to have drawn a line at light speed, and what it means that the mathematics points so clearly to a world on the other side of that line. A world that remains stubbornly out of reach. The silence from our detectors, it might not mean we're done. Maybe we've been looking in the wrong places. Or for the wrong kind of signal. What if the evidence for tachyons isn't in a lab at all, but written across the sky? Some theorists have started looking at the most violent events in the cosmos. The most energetic, wondering if these theoretical particles could be hidden actors there. Take gamma-ray bursts. These are titanic explosions, distant stellar cataclysms. They flood the universe with more energy in a few seconds than our sun will emit in its entire lifetime. The mechanisms behind them are still debated. But could a cascade of tachyons born in the heart of such an explosion, moving with that impossible speed, could that contribute to the bizarre energy profiles we see? If tachyons decayed into normal particles as they traveled, their backwards time journey might imprint a strange signature on the light that reaches us. A faint echo. An echo of inverted causality coming from the edge of the observable universe, and this speculative bridge it goes even further, to the greatest cosmic mystery now, dark energy. We know the universe's expansion is accelerating. Something is pushing galaxies apart with ever-increasing force. We call that something dark energy, but we don't know what it is. Here, the tachyon idea takes a radical turn. In some advanced frameworks like string theory, physicists describe a hypothetical state, a tachyonic condensate. Imagine a field that permeates all of space, but a field whose fundamental quantum is a tachyon. This isn't about individual particles zipping around. It's about the very fabric of the vacuum having a tachyon-like nature. In this model, the energy inherent in this pervasive field, that could be the driver of cosmic acceleration. The repulsive gravity of this everywhere present tachyon stuff could be what's forcing the universe to expand faster and faster. It's a breathtaking connection. A particle defined by moving faster than light could be the hidden engine behind the fact that space itself is stretching faster than light on the largest scales. These ideas are highly speculative. They live at the furthest frontier of theoretical cosmology, where mathematics runs ahead of any conceivable experiment. But that's their value. The Tachyon hypothesis is more than a quirky footnote. It's a powerful probe, a thought experiment made solid by equations. By asking what a universe with faster-than-light particles would look like, physicists are forced to re-examine everything. From the fate of stars to the destiny of the cosmos, it creates a bridge between the infinitesimally small world of quantum particles and the astronomically large canvas of the expanding universe. Each speculative link, to gamma-ray bursts to dark energy, it isn't a claim of truth. It's a question pressed against the darkness. If the walls of reality are porous, what else might slip through? The search for the tachyon, in the end, is a search for the limits of physics itself, testing whether our most cherished rules are laws or just local customs. The universe already has a kind of faster-than-light connection. It's real, it's proven, quantum entanglement. Two particles get linked. You measure one, and the state of the other is instantly defined. Any distance, a light year, a billion light years, the effect is immediate. Einstein called it spooky action at a distance, because it seemed like an influence traveling faster than light. And in a sense it does. The correlation is instantaneous, but after decades of debate and experiments, physicists have a consensus. You can't use this spooky action to send a message. You can't transmit information or a command or a single bit of data faster than light. The reason is subtle. When you measure your entangled particle, the result is random. You have no control. Your friend, light years away, gets a correlated result instantly. But from their perspective, they just see a random outcome too. Only when you both compare notes later, using a slower communication channel, do you see the spooky correlation. No signal traveled between you faster than light. The causal structure, the light cone, stays intact. Entanglement shows a profound interconnectedness, but it respects the cosmic speed limit for information. Now, the tachyon. The tachyon isn't about correlation. It's proposed as a physical carrier, a bullet of information. If you could modulate a beam of tachyons, you could send a deliberate message. A word, a picture, an instruction from point A to point B, faster than light. And because of the relativistic link between speed and time, that message could arrive before you sent it. That's the fundamental distinction. Entanglement is a ghostly whisper of connection that can't shout into the past. A tachyon would be a cosmic telegram stamped with yesterday's date. One is a weird but accepted feature of the quantum world. The other is a hypothetical wrecking ball aimed at cause and effect. Placing them side by side shows the line physics walks. We've accepted phenomena that defy classical intuition. Yet we hold the line at phenomena that would shatter the logical sequence of the universe itself. The tachyon forces the question, is that line a permanent wall or just a frontier we haven't crossed yet? That link between speed and time, it leads to this thought experiment. A device called the Tachyon Anti-Telephone, a classic model in theoretical physics, a machine that could send a message into your own past. Here's how it would work. You have a transmitter and a receiver. They're separated by 1 light year. You send a tachyon signal. It travels faster than light, so it doesn't take a year to arrive. From your point of view, it arrives at the distant receiver in 6 months. But in relativity, that speed twists time. For the signal, the journey might end 6 months before you pressed send. The distant station gets your message. It immediately sends a confirmation reply back using ordinary radio waves, light speed. That radio reply takes a full year to crawl back. You do the math. You sent the tachyon signal at time 0. The tachyon arrived at the distant station at time -6 months. The radio reply left at -6 months. Traveling for 1 year, it arrives back at your location at time +6 months. The result is a loop. You receive the reply to your message 6 months before you decided to send the original. The confirmation of receipt precedes the act of sending. This model, the antitelephone, it crystallizes the communication paradox. It's not just about speed. It's about sequence. It forces a confrontation with the logical bedrock of the universe. Could it ever be built? The mathematics of tachyons says maybe. The physics of causality screams no. The antitelephone isn't a blueprint, it's a stress test, a way to push the implications of a theory to their breaking point. To see what holds, it asks whether our laws prohibit this kind of loop, or if our understanding of those laws is incomplete. Does nature have a hidden clause that prevents the antitelephone? Or does it merely wait for a technology we cannot yet conceive? This tiny machine, existing only in thought, it holds a mirror up to the deepest assumptions. About time, about reality, about the very possibility of a universe that makes sense. That antitelephone, in a vacuum as a thought experiment, it shows the paradox in its purest form. But the tachyon idea didn't fade, it transformed. In the most advanced physics now, the word has a new life, a very different one. It's less about a particle you could catch, more about a state for the universe itself. This is the tachyon condensate. In string theory, which tries to weave gravity and quantum mechanics together, a tachyon often signals an instability. A pencil balanced perfectly on its tip. That's an unstable state. The slightest breath, the tiniest vibration, and it falls. In string theory, there are these complex, multidimensional objects. D-branes, they can exist in such precarious states. The math for their instability uses the exact same formalism, the same equations that describe our hypothetical faster-than-light particle. So physicists use the term tachyon for this tipping point condition. The process of falling from that unstable point to a stable one is tachyon condensation. It's a cosmic settling, a phase transition for reality. Think of water freezing. Above a certain point, water molecules move freely. Below it, they lock into a crystal. The moment of freezing is a condensation into a new, stable order. In this string theory picture, tachyon condensation might describe the early universe. Cooling from a seething, symmetric state into the structured cosmos we see, with distinct forces and particles. It's a story of cosmic decay leading to cosmic creation. So the tachyon has evolved. It began as a speculative bullet of causality. Now it's a sophisticated mathematical tool for describing how the fabric of reality might rearrange itself. This shows the dynamic nature of theoretical physics, a living nature. An idea isn't just right or wrong, it's a probe, a set of equations that can be repurposed to ask entirely new questions. That haunting possibility of a time-traveling particle opened a door in our understanding. And even if that specific particle never appears, walking through that door led theorists to landscapes they never expected. The journey of the concept itself is a kind of time travel, an idea from the past continuously reshaping our vision of the future. An egg once scrambled won't unscramble. That's a kitchen fact, but it's also a truth about the universe. The arrow of time, it points forward. It's governed by the second law of thermodynamics. Entropy, disorder always increases in a closed system. Things go from order to chaos. That's why memories are of the past, never the future. It's why time feels like a one-way street. So then, how could a particle travel backwards? Wouldn't that unscramble the cosmic egg? The answer is a subtle distinction. The tachyon's backwards journey isn't about reversing entropy. It's not a smashed glass leaping back onto the table. That would violate thermodynamics. Instead, the tachyon's relationship with time is a geometric property, a consequence of how it fits into space-time. From our perspective anchored in our slower-than-light reality, the tachyon's clock appears to run backwards. Its cause seems to come after its effect. But from the tachyon's own point of view, if it had one, time might flow normally, forward. Its own entropy might increase. Its own eggs would scramble. The paradox only happens when we try to stitch its timeline onto ours, when we try to make two different kinds of existence line up in a single story. This forces a deeper question. Is the arrow of time a fundamental law woven into reality, or is it an emergent phenomenon, a large-scale statistical tendency? Like a crowd flowing in one direction, even though any single person could move against the current, our experience of time's flow could come from being made of trillions of particles interacting in irreversible ways. The universe, on average, becomes more disordered, but a single exotic particle, operating under different rules outside that average, could it slip through a crack in that direction? Could it be the one person walking upstream while the crowd surges downstream? Exploring this doesn't just challenge the tachyon. It challenges our basic assumptions. It asks if the direction of time is a universal truth, or just the most probable outcome in our corner of a much stranger cosmos. Stephen Hawking saw those equations differently. He saw a lock, not a doorway. He proposed a safeguard chronology protection. It's an elegant idea. The universe has a vested interest in its own history. It can't allow paradoxes, those logical knots that unravel cause and effect. So the laws of physics, they must conspire to prevent true time travel, not by forbidding it in theory, but by making it impossible in practice. Any attempt to build a machine with tachyons or warped space would trigger its own destruction. A built-in security system. The moment you try to twist time into a loop, quantum physics responds. The vacuum of space isn't empty. It seethes with fleeting particles, quantum fluctuations. Hawking suggested that in the distorted geometry of a time machine, these fluctuations would feed back. A particle travels back a fraction of a second, interacts with its past self, amplifies the fluctuation. That amplified version travels back, interacts again, grows stronger. The process runs away. An infinite surge of energy in an instant, a firewall of quantum fury, vaporizing the machine before the first paradox is born. It's a fail-safe, a law of cosmic self-preservation. Hawking's conjecture isn't a proven theorem, it's a powerful argument from a deep thinker, a philosophical stance. That the universe might favor a single, consistent story, uneditable, where effects follow causes and the past remains fixed for our tachyon, this is a formidable barrier. It suggests that even if the math permits a particle to travel backwards, the universe itself might have a veto. Any configuration of matter trying to harness that property for a signal for an antitelephone would meet that quantum firewall. The timeline would be protected. History would remain coherent, so the question shifts from, can we build it, to, does reality allow it? Hawking's idea implies the answer. A gentle but absolute no. In 2011, the opera experiment sent a shock through physics. A team in Italy announced they'd measured neutrinos arriving from Switzerland faster than light could travel the same distance. The margin was tiny, 60 nanoseconds over 454 miles. But if it was right, it meant a crack in Einstein's relativity. Headlines said the speed of light had been broken. Time travel suddenly felt less like fiction, more like something waiting to be announced. For a moment, the tachyon seemed plausible, maybe even already found, hiding as the neutrino. The reaction from other scientists was intense skepticism. Extraordinary claims need extraordinary evidence, and this was the most extraordinary claim you could make. Labs everywhere began dissecting the result. They looked for overlooked variables, subtle environmental effects, any possible error in the timing, which was precise to billionths of a second. It was a global audit of one measurement. Months later, they found the problem: a loose fiber optic cable in the GPS system that synchronized the clocks. A faulty oscillator. Human-scale errors in an experiment measuring across hundreds of miles. The neutrinos were exonerated. They hadn't broken the speed limit. The pillar stood firm. This is how science corrects itself. The initial announcement wasn't a failure. It was a necessary step. The researchers published their astonishing data and invited the world to prove them wrong. And the world did. That self-correcting mechanism, that commitment to evidence over excitement, is what separates science from speculation. For the tachyon hunt, the lesson is profound. It shows the immense difficulty of measuring something that defies our basic understanding of motion. If a loose cable can create the illusion of superluminal speed, then any future claim has to survive a hurricane of doubt. It has to be verified by multiple, independent experiments using different methods. The opera incident didn't kill the tachyon idea. It placed it in a kind of suspended animation. A healthy tension between mathematical possibility and physical reality. It reminded everyone that the universe guards its deepest secrets fiercely, often behind layers of human error. The next time a headline screams about faster-than-light particles, we'll remember the neutrinos that weren't. And we'll know the real discovery will only come after the world has tried and failed to prove it a mistake. Black holes are these ultimate paradox engines. They take gravity, everything we know about it, and smash it right into quantum mechanics. And what you get is this deep conflict. The information paradox. You throw a book into a black hole and the book is gone. But quantum mechanics says the information, the arrangement of atoms, the words, it can't be destroyed. It has to be preserved. So where does it go? It's not just about the book. It's this principle that the universe keeps a perfect record. And a black hole, according to the old theory, doesn't. It evaporates over eons. It leaves behind this featureless radiation. The record is erased. So physicists have proposed these wild ideas. One is the black hole firewall. A wall of energy just inside the event horizon. It incinerates anything falling in. The information gets preserved in the chaotic aftermath. It's a drastic fix. Like the universe building a cosmic incinerator to protect its accounting. But it creates new problems. It violates the smoothness of spacetime. Relativity says spacetime is smooth. So then, into this search steps an old theoretical friend. Could tachyons offer a way out? Some models are speculative. They suggest the warped geometry near the event horizon might allow exotic quantum states. States where information doesn't travel out through space. It could travel backwards through time. From the outside, that's what you'd see. Imagine the information from that book. Not encoded in radiation leaving in the far future, but in particles that tunnel backwards along their world lines. From our timeline, they'd appear to be emitted before the book even fell in. It's not a physical rescue. It's a causal rearrangement, a rewiring of the sequence, so the information was never truly inside the black hole to be lost. It was always imprinted on the boundary or on the radiation, but in a scrambled, time-inverted way. This is fringe of the fringe physics, a hypothesis built on a hypothesis. Its value isn't in being correct. It's in showing the lengths you have to go. The stretches theoretical physics must make to solve its deepest puzzles. The tachyon, a solution to one paradox of motion and time, becomes a tool for another. For the paradox of information and gravity, it weaves a thread between two separate mysteries. It suggests the universe's strangest corners might be connected, by principles we haven't named yet. If reality allows particles that experience time backwards, then maybe it also has a built-in mechanism to ensure no story is ever truly forgotten, not even one swallowed by a black hole. The idea of a fixed or malleable past, it goes right to the heart of how we live. We operate on this quiet belief that our choices matter, that the future is open. But if you allow for influence from the future, even just in theory, that belief starts to feel less solid. If a tachyon from tomorrow is part of what happens today, then the moment we call a choice isn't a fresh start. It's more like a point in a loop, a knot that was already tied. That's the philosophical weight of it. It makes you confront free will. Are we writing the story, or are we reading from a script where the last page already exists? The tachyon idea doesn't answer that. It just gives the old debate a new language. It asks if our sense of agency is an illusion, something that comes from our limited, slower-than-light point of view. From inside the story, the plot feels open, but from outside of time, maybe every turn was always there. This isn't about fate, it's about consistency. The Novikov principle, the one we talked about earlier, offers a kind of resolution, a universe that's a single, self-consistent block. In that view, your choice to watch this, and any tachyon that might have influenced it, they're part of the same fixed tapestry. Your will is free, but what it does is woven into a whole that doesn't contradict itself. You're not a puppet. You're a necessary thread, so the question shifts. It's not, can we change the past? It becomes, what does it mean for the past to already include our attempts to change it? It's a dizzying recalibration. Some philosophers push back, though. They say if tachyons have no physical reality, if they're just elegant solutions in a notebook, then they don't tell us anything about the world. They're mathematical ghosts, intriguing but empty. To build a philosophy of time and will on them is to build a castle on a cloud. so the debate rests on a razor's edge. It asks what we consider real. Is it only what we can measure? Or do the unshakable implications of our best theories also shape reality by showing its logical shape, its hidden possibilities? The tachyon lives in that tension. It may never be found, but by its very conceptual possibility, it's already changed the landscape of thought. It's shown that our classical intuition of a linear, independent timeline, that's not a necessary truth. It's a contingent experience. That might be its greatest gift, not as a potential particle but as a mirror held up to our deepest, unexamined assumptions about cause and choice and the flow of time. By threatening to break the rules, it reveals how deeply those rules are etched into our understanding of what it means to be and to act in this universe. So the search is for more than a particle. It's a search for the boundaries of our own imagination. The weight of paradox, the silence of experiments, it leads to a simpler idea. Maybe tachyons just aren't real, not as particles we could ever detect. Causality, the idea that cause comes before effect, it's woven so deep into physics. To throw that out, you'd need overwhelming evidence, and we don't have it. This skepticism, it's not about dismissing curiosity, it's the scientific method. When a beautiful mathematical idea never shows up in reality, you question the idea. You don't question reality. So where do you look instead? Often, things that seem to hint at faster than light travel, they have more ordinary explanations. Still fascinating but ordinary. Take quantum tunneling. An electron appears on the far side of a barrier it shouldn't cross. In some setups, the math can suggest the particle's wave function gets across faster than light could. That sparked talk of superluminal tunneling, but most physicists see that as an illusion, a misapplication of the idea of speed to a quantum process. The particle isn't a bullet taking a shortcut. It's a probability wave existing on both sides at once. The tunneling time isn't travel time, it's a measure of interaction. So what looks like breaking a cosmic law is really just quantum weirdness working within the rules. This pattern keeps repeating. An anomaly appears. It seems to threaten causality. Then, with deeper scrutiny, a new understanding emerges, one that preserves the causal structure. Physics has a history of these moments, and each one reinforces a kind of philosophy. If a theory allows for time travel paradoxes, the theory is probably incomplete. It's missing a piece, a hidden mechanism or a correction that will restore consistency. That drive to fix the model, to find the missing piece, it's a powerful engine. It forces innovation. It led to ideas like Hawking's chronology protection. It pushes theorists to refine string theory to avoid unstable states. The search for tachyons has value even if it never finds one, because it stresses our models to the breaking point. It shows us where the cracks might be, and so it shows us where we need to build stronger foundations. The prevailing sentiment isn't closed-mindedness. It's a respect for the universe's logical coherence. The cosmos seems to be a place that makes sense, where stories have a beginning, a middle, and an end. Until a particle arrives stamped with yesterday's date, that's the story most choose to believe. And in that choice, there's a different kind of wonder. A trust in the fundamental order we're trying to understand. But that logical order, it's only one part of the story. There's always been this other narrative, running right alongside the equations. Science fiction. For decades, its stories have been full of warp drives, time machines, particles that break the rules. Tachyons are a staple, and a physicist might wince at the technical liberties, the beams, the pulses, the simplified magic. But they understand the deeper value. These stories aren't about accuracy, they're about ignition. They ask that very first question, what if? That question is a spark. And for so many young minds, that spark landed on dry tinder. A child watches a starship vanish into a tachyon corridor. A teenager reads a novel where a scientist uses tachyons to send a warning to the past. In that moment, the cosmos isn't a collection of distant points of light. It's a playground, The rigid laws from the textbook feel less like walls and more like a challenge. That emotional hook, that sense of wonder, it's irreplaceable. So many researchers now, the ones probing string theory or analyzing cosmic ray data, they first fell in love with physics through these fictional gateways. The narrative gave them a language for their curiosity, long before they learned the mathematics to refine it. And this creates a dialogue, a symbiotic one. Fiction dreams with audacity. It visualizes the impossible, gives abstract concepts a face, a drama. Science, in turn, takes those dreams and subjects them to the rigorous test of reality. It asks the hard questions fiction can gloss over. What about causality? What about entropy? Where does the energy come from? This back and forth, it enriches our culture. It keeps complex ideas alive in the public imagination. It turns dense theoretical papers into conversations at the dinner table. When a new physics headline breaks, the public isn't starting from zero. They have a framework, however fanciful, to begin understanding. They're already invested in the mystery. This ongoing conversation, it ensures the deepest questions about time, about our place in the universe, they never grow stale. They stay vibrant, urgent parts of our collective story. The child inspired by a comic book today might be the one who, 30 years from now, designs the experiment that finally closes the book on tachyons. Or, against all odds, finds them. Either outcome would be a triumph born from that first fictional spark. That empty space between atoms, it's not really empty. It's this seething, bubbling foam. The rules we know, they loosen there. Particles and their antimatter twins, they can just appear. They borrow a little energy from the vacuum, exist for a moment, then annihilate. Pay the energy back. These are virtual particles, they're not illusions, they're part of the math, quantum field theory. That's what describes the universe at the smallest scales. Their brief existence, it's why we have forces, like the Casimir effect. Two metal plates in a vacuum, pushed together by the pressure of these quantum fluctuations. It's validated, strange but validated. So then the question, in that haze where the impossible becomes possible for a moment, could virtual tachyons flicker into being? Could the quantum foam have bursts of faster-than-light travel? Some readings of the math say yes, for a time so short it's almost meaningless, a slice measured in units like the Planck time. A decimal point, then 43 zeros, then a 1. The equations allow for virtual particle pairs where one might act like a tachyon, a ghost of a ghost. A temporary anomaly in spacetime, it would vanish before it could be measured, before it could carry a signal or create a paradox. That's the crucial distinction. A real, detectable tachyon that's permanent. It could carry information, shatter causality. A virtual tachyon is a temporary fluctuation in a field. It's part of the underlying quantum static. The background noise of reality, where all forces come from. It doesn't violate causality because it's fundamentally unobservable as a single event. You can't intercept it. You can't decode a message from it. Its influence is only felt in the aggregate. In the subtle ways it might contribute to the forces that hold things together. That subtlety, it shows the ingenuity of physics. It finds a way to accommodate the mathematically possible, even the bizarre, inside a framework that protects the logical order we experience. The quantum vacuum becomes a sandbox, where the universe can play with every idea, even backwards time, but only under strict, self-canceling rules. It provides a counterpoint. It suggests superluminal phenomena might not be entirely forbidden. They could be woven into the fabric of existence, but at a level so fundamental and transient that they build up the stable, causal world we live in. They don't tear it down. The dream of a tachyon telegram, it fades into the quantum static. But in its place, you get an insight. The walls of reality aren't solid. They're alive with momentary possibilities, each one a whisper of a different set of rules. Our classical universe of cause and effect, it's not the whole story. It's the calm, averaged surface, on a deep and turbulent quantum sea. Instant communication across the galaxy would be the beginning. You could send a message to a colony 1,000 light-years away, get a reply all in an afternoon. That delay, that isolation from light speed, it would just disappear. Civilizations could talk in real time, connected across the void. But it goes beyond conversation. Think about a computer. Its basic job is moving information from one place to another. Now put in a tachyon network. Information wouldn't just move through space. It could be sent into its own past. A result could arrive before the calculation that produced it even started. That's not just faster processing. It's inverting the sequence of logic. A machine like that could solve problems we can't even state, by using answers that are already there. It would be an oracle, looking into a loop of cause and effect. But that power has a shadow. A tachyon communicator in the wrong hands is the ultimate weapon. A military could get intelligence from tomorrow's battlefield. They could launch a strike knowing an enemy's future movements. The idea of a surprise attack becomes meaningless. Conflict turns into a hall of mirrors, where every action is preempted by a reaction sent from further ahead. It's a permanent, paradoxical war where the first move is always the last. This thought experiment isn't a blueprint, it's a mirror. It shows our ambitions, our fears about technology. We dream of connection, of limitless knowledge, but we see how those tools can be twisted into control, into devastation. Maybe that's why the universe has a safeguard. Stephen Hawking's chronology protection, that quantum firewall that destroys time machines before they exist. It might be more than a physical law. It could be a kind of cosmic wisdom. A blessing. By making true backwards time travel impossible, the laws of physics might be protecting us from ourselves. They stop a reality where every breakthrough carries the seed of its own catastrophic misuse. They make sure progress has to move forward into an unknown future. We can't go back to fix mistakes or to get an unfair advantage. We have to live with the consequences of our choices in one coherent timeline. That constraint isn't a limitation. It's the foundation of meaning, of responsibility. It's what makes a universe that makes a consistent kind of sense. So the silence from our tachyon detectors, that's not a disappointment. It's a quiet assurance. Some doors are meant to stay closed. A paradox is a closed loop. A knot that can't exist. But maybe the universe just doesn't tie the knot. There's a popular way out of these dead ends, the multiverse. The idea is simple and it's staggering. If a tachyon went back and changed one event, stopped a meeting, it wouldn't rewrite our history. The timeline would branch. At that moment of intervention, reality splits. One universe continues just as it was. The meeting happened, you exist. Another universe peels away. The meeting never occurred. A different version of events unfolds. In that new branch, the tachyon's arrival wasn't an intrusion from the future. It was a natural event from its own past. The paradox evaporates. Cause and effect stay consistent inside each timeline. Every possible outcome of every tachyon interaction becomes real somewhere. The cosmos becomes a tapestry. Infinite variations. Every choice, every chance event spawns a new world. This sidesteps the grandfather paradox. It sidesteps Novikov's self-consistency principle. It doesn't need a single, fixed timeline. It offers a cosmic architecture of endless possibility. For the tachyon, it's a perfect home. Such a particle could zip backwards through time, not as a wrecker of history, as a seed for a new one. Its very journey would be the event that catalyzes a new branch. In this framework, tachyons aren't dangerous, they're creative forces, weaving new threads into an ever-expanding multiversal fabric. But this solution has a cost. A profound cost. It trades a paradox for an infinity. If every possible outcome is realized, the cosmos isn't just vast, it's endlessly proliferating. For every decision you make, a universe exists where you made the opposite choice. For every particle interaction, every quantum fluctuation, reality splits. This is a staple of science fiction, some interpretations of quantum mechanics. It remains one of the most speculative ideas in theoretical physics. There's no experimental evidence for other universes. By definition, they'd be causally disconnected from our own, forever beyond our reach. Its value isn't in proof, it's in demonstration. The multiverse hypothesis shows the lengths the human mind will go to preserve logical consistency. Faced with an idea as disruptive as backwards time travel, theorists don't give up. They imagine a cosmos so generous, so expansive, it can accommodate anything without breaking. It offers a framework, a place where the mathematics of tachyons could be physically real, without threatening the stability of our own familiar world. The tachyon, in this light, becomes less of a particle, more of a key that might not open a door in our wall, but one that could unlock an entirely new room. In a mansion of realities we can scarcely comprehend, Orpheus went down into the underworld. He played music, a plea to the rulers there, and they gave him a chance. He could lead Eurydice back to the world above, but with one condition: he couldn't look back at her, not until they both reached the light. It's a story of unbearable tension. The past is right behind him, the future is the path ahead. But then in a moment of doubt, love, fear, he turns, he looks, and she's gone, lost forever. That myth, it captures something, a human truth. This desperate desire to reach back through time, to undo a single moment, to take back what's gone. That ache isn't just in Greek poetry. You find it everywhere. Cultures across the world, throughout history, they tell these tales. Tales that bend time. Break it, prophets who see the future in dreams, heroes who travel to ancestral realms, oracles giving warnings, trying to change a fated path. These stories, they're like our first thought experiments. About cause and effect. They're about the weight of knowing what could be, the torment of not being able to change what was. The Tachyon idea comes from that same line. It's not a break from ancient wonder. It's a continuation, just with new tools. Where Orpheus had his grief, his glance over the shoulder, Gerald Feinberg had the math. Special relativity. The desire is the same: to challenge the flow, the irreversible flow of events, to ask if the past is really set, or if there's a thread, something subtle, you could pull to reshape it. Our myths used gods and magic to explore this. Our physics uses imaginary mass, light cones. The language changed, from poetry to equations, but the central question, it's the same. Echoing for millennia, what does it mean to be bound by time, yet always dreaming of the other side? This connection, it's more than just poetic. It shows something. Our scientific questions, they aren't cold calculations. They come from the same place, the same deep well of curiosity and longing that made our myths. The physicist looking for a vacuum Cherenkov glow. The shaman seeking a vision of tomorrow, they are on the same fundamental quest, both trying to peer beyond the veil of the present. To find a crack in the wall of sequential experience, seeing that link, it reframes everything. It's not just a technical puzzle about particles. It's a chapter in the long human story of trying to understand our place in a universe ruled by time. If you put the Tachyon equations next to the Orpheus myth, you see two different maps of the same territory, the territory of human limitation and the hope that we might transcend it. The myth warns of the cost, loss, paradox. The mathematics warns of causality violation. Quantum firewalls. Both are explorations of boundaries. They remind us the rules of time aren't just physical laws to study. They are the framework for love, loss, memory, choice. Our drive to test those rules through story or science, maybe that's one of the things that makes us human. It's a stubborn refusal, a beautiful refusal. To accept that the story can only be read forward, never rewritten. We think the past is fixed, that it's done. You drop a glass, it breaks, the pieces don't fly back together. You send a message, the reply comes later. Never before. That feeling, it's strong. It comes from everything we've ever seen. Our brains build a model from that. And it's a good model for the world we live in, but that world is specific. It's the world we can touch, where things move slowly compared to light. Where gravity is just this steady pull. That's Newton's world, his laws describe it. They feel right because they match what we see. An object keeps moving. Every action has an opposite reaction. It's clockwork, predictable. Step outside that, though, and intuition breaks. It breaks completely. At near light speed, time stretches. Space contracts. It makes no sense to our everyday minds. Then there's the quantum world. Particles in multiple places at once. Behavior ruled by probability, not certainty. These aren't just ideas. They're the foundation. Relativity, quantum mechanics. They're counterintuitive, but they work. They're our most accurate picture of reality. The universe doesn't have to feel right to us. Our brains evolved for the savannah, for spotting predators, for judging the arc of a thrown rock, not for parsing four-dimensional spacetime, not for quantum superposition. Tachyons come out of the math of these theories. They're not a fantasy. They're a logical possibility. You take relativity seriously. You follow its equations into places they weren't meant to go. And this is what you can find. Particles that move backward in time. Signals that arrive before they're sent. That this clashes with our instincts, it's not a flaw in the math. It's a revelation about us. Our discomfort is a sign. It marks a boundary between the world we evolved to see and the universe as it might actually be. The lesson is humbling. The cosmos follows its own rules, not the rules of human story, not what feels right. What seems like a paradox to our minds might just be a different logic. A pattern in reality we're only starting to see. So the search for tachyons, it's more than looking for a particle. It's a test. Can we trust the strange, beautiful language of mathematics over the loud, insistent voice of our own intuition? The silence from our detectors, it's not an ending. It's a narrowing, a focusing of the search. Future experiments are being designed now with a sensitivity that's hard to even picture. Upgrades to the Large Hadron Collider, and maybe even more powerful accelerators one day, will push into higher energies. In those collisions, the fabric of spacetime gets stressed. And if tachyons are real, they might flicker into existence there in the debris. Energies that echo the first moments of the cosmos. It's a hunt for ghosts, but we're building better ghost detectors. We're also looking outward to the sky. New astrophysical observatories, instruments that can dissect light across the whole spectrum. They're like new telescopes for this. They'll scan the heavens for anomalies, a burst of radiation with the wrong energy, a cosmic ray event that doesn't fit any model. The faint, impossible glow of vacuum Cherenkov radiation from an empty patch of space. They're listening for a whisper in the cosmic static, a single note that doesn't belong, and in theory the landscape is shifting. The work to unify quantum mechanics and gravity, that forces a re-examination of every assumption. Frameworks like string theory, the holographic principle, they're building new visions of the cosmos. Dimensions that curl, information painted on a boundary. In these models, the tachyon's signature often comes back, not as a particle, but as a signal of instability, a marker of a cosmic phase transition. Theorists are working to see if these constructs can allow a stable, causal form of faster-than-light travel, or if they banish the idea for good, proving it was a beautiful mathematical phantom all along. That's the rhythm of this. Each experiment that finds nothing, it sharpens the question. It tells us where not to look. Each theoretical breakthrough, even one that closes a door, cracks open a window onto something stranger. The journey isn't over. It's evolving. The search for a particle that travels backwards in time has become a deeper probe into the nature of time itself, into causality, into the logical structure of the universe. This mystery, from a few lines on a page, it'll engage the most brilliant minds for generations. Because at its heart, it's asking the most human question. Are the rules we live by the only rules there are? That ghost in the equations. It's taken us from a few lines of algebra to the edge of black holes, through logical paradoxes, out to the idea of a multiverse. The tachyon, this particle that could, in theory, move backward in time, it's still just a theory, a kind of shadow that our own math throws. We haven't found it. The detectors hear nothing. Our biggest collisions show no sign. It's a possibility the universe, for now, doesn't seem to use, but calling that a dead end misses the point. The value was never about catching it. It's about the questions it makes us face. By existing on paper, it forces us to look at our own assumptions, to defend cause and effect, to push engineering, trying to find something that might be unfindable. It keeps a certain kind of wonder alive, the wonder about a cosmos whose rules we might not fully know yet. This search, whether we find something or just understand why we can't, it stretches what we know. The edges of our maps aren't borders, they're invitations. The next big thing in physics won't come from checking what we already expect. It'll come from a question that seems impossible at first. A question like the one a backward-moving particle asks. When we look at the stars or into the quantum foam, that spirit of asking is the main tool we have. So what's on the other side of that speed limit? Is our universe bound by strict cause and effect? Or is it stranger, more layered than we've imagined? Let us know what you think. And if you want to come along for more of these journeys into space mysteries, subscribe.